So it is a warm welcome to everyone. We have Nithyasri ma'am here. Ma'am, first we will do an informal like mic and video check of yours if it is working properly, and then we will invite our host so that we can start with your keynote talk officially. So I request Nithyasri ma'am to please on and her mic and video for the video check, please.
Sure, Ryan. Good morning.
Good morning. You look great. Hi, ma'am.
Hello.
Your video is visible and your voice is also good.
Great.
Thank you, ma'am. Thank you. We can start officially now. Yes.
So it gives me immense pleasure to extend to you a very warm welcome to day one of eSummit 21 on behalf of IIIT Info Communication Incubation Center. With a scintillating start on day 0, this day has even more to offer. We will dive into the exhilarating world of quantum computing, AI, and robotics. So keep your anticipation and curiosities high, as we have prominent speakers from most advanced organizations and universities to apprise us about their areas of expertise. We have keynote talks, panel discussions, and workshops lined up for you today. So we will be starting with some enlightening keynote talks. For this, first on board, we have with us Nithyasri Srivathsan. She is the CEO and founder of SheQuantum, which is an amazing initiative to attract more women to the field of quantum computing. She is also the author of a bestseller, Quantum Computing, an Unconventional Beginner's Book. So please welcome her. Ma'am, please.
Let me just share my screen.
Oh, yeah, sure.
Can you view my screen?
Yes, ma'am, it's visible.
All right. So, yeah, great. So, a very good morning to all of you here, and I'm very happy to be here today. Thank you, IIIDA, for inviting me to talk about one of the most exciting topics, quantum computing. And I'm very happy to see that this eSummit is focusing on, the emerging technologies like AI, data science, ML, robotics, and more interesting to me is quantum computing, and that's what I'm here to talk about today. So let's just set the seriousness of this field straight before we jump in. And this field is a field of versatility. This field is a field of opportunities. And that is what is the best part of quantum computing. And, just to set again the seriousness straight, last year in our union budget, $1.1 billion was allocated only for quantum computing research in India. That is the level of seriousness of this subject. And of course, that should tell you that there are plenty of opportunities and scope for this field. And of course, to say, multinational companies like IBM, Microsoft, they're investing tons and tons of money on this quantum computing research, and that's why I think this is the most appropriate time for youngsters to explore this field and take it up as their careers. So in my talk, what I'll be doing is to convince you to pursue this field, and I hope you will. So let's jump right in. So what is quantum computing for starters? So quantum computing is basically a science that uses the laws of quantum physics to perform computations. So the main distinction and difference between the computer, the classical computer that you're using now to view my talk, and a quantum computer is that in a classical computer, we use what are called bits. And of course, they are zeros and ones. And you can also take the analogy of a switch wherein you see the off or the on positions, right? So what is different about quantum computers is that they use what are called quantum bits, which we fondly call as qubits. And these guys, right, they're very interesting people. They can exist in 0 and 1 states simultaneously. And that is what is called a superposition. I hope you will be familiar with that word, superposition, from your quantum mechanics classes, and it's also called a linear combination. And this is what all the hype is all about. This is what gives you the advantage over classical computers. This is what gives you an edge in the computational speeds, right? And what is more important to see is that let's say that you are majoring in physics, you are majoring in computer science, you're majoring in electronics, you're majoring in biology, even finance. You can contribute to this field. That is the beauty. And just to give you an idea of how interdisciplinary this field is, there are I'll tell you two examples. One is quantum computing for drug discovery in biology, and it's very interesting because nobody would have thought quantum computing and biology can come together. And I can give you a very nice example for this. Development of COVID-19 vaccine. If we had a fault-tolerant, an ideal quantum computer that we have in theoretical paper now, we would have been able to discover the vaccine in a much more quicker pace. And the other example that I want to give you is of finance. This is a field that is picking up a lot lately. It's in the trends now. Quantum computing for finance. And see, that's the versatility of this field. That's the interdisciplinary nature of this field. So what I want to tell you here is that each and every one of you listening to my talk now can contribute to quantum computing, and I strongly urge you to explore it and start to learn it. Right. So now let's go on to a more serious technical talk. So, what are qubits? Right, quantum bits. We are going to do this in a very nice way. We're going to look at look at from two perspectives. One mathematically, the other one physically. So when you see in mathematics, what you can do with qubits is that qubits are matrices or vectors. That's how you look at it. And when you see from the eye point of physics, what you say is that qubits can be represented as the spin of an electron or the polarization of a photon. So in the next few minutes, what we're going to be doing is to draw a parallel between these three and use the phenomenon of measurement to understand these two, spin of electron, polarization of photon, and relate it with vectors and matrices. So let's jump right in. This is a very neat little experiment to find spin of electron. It's called the Stem Gerlach Apparatus that we're going to use. And what we're going to do essentially is a very simple experiment. We have a source of silver atoms. I pass the beam between my poles of a magnet. Now, you should ask me one question. Why are you not using an electron beam? Because we are trying to find the spin of an electron. This is for a very obvious reason that moving charges will be affected by magnetic fields, which we don't want. We are going to be using a beam of silver atoms, and it's convenient because your silver atoms has one electron in its outermost shell. So that comes across as convenient for us. So let's look at two cases. Before that, you should know one thing. We measure in the vertical direction. All right, that's something you should understand and remember for the next few minutes. So let's take the case one. Your electron is aligned its north pole closest to the south of the magnet. What happens? North and south pole, an obvious attraction, and there's a deflection upwards. What happens in the second case is that your electron, its south pole is close to the south of the magnet, obvious repulsion, and a downward deflection. This is very simple and straightforward, but what is more interesting is what comes next. What we're trying to do here is to repeat this apparatus multiple times, and for the sake of ease, let's take 2 times. So I have a Stem Gerlach apparatus here and another one just next to it. Now what I do is to pass the beam of silver atoms. I see, let's say I observe a downward deflection in the first apparatus, and then in the second apparatus I do this again. I again see a downward deflection. Now what you have to understand is that I am doing the measurement in the vertical direction both the times, and when I keep repeating this 100 times, 1,000 times, infinity times, it's the same result because I'm not changing my direction. I'm not changing the condition of my measurement. So what happens in case 2 is that I take 2 apparatuses, but what is different is that now in the second apparatus, I take a horizontal measurement. So just to make you understand what vertical and horizontal measurements are, this is vertical, 0 degrees, and this is horizontal, 90 degrees, perpendicular. So that's how you should understand how vertical and horizontal work. So what you see here is very interesting. Let's say you get a deflection upward in your first apparatus. What you notice in the second apparatus is that you have a probability of half to get an upward deflection as well as a downward deflection. So the point that is a take home is that when you change the condition of measurements, your measurement also sees a change. So let's do this with the polarization of a photon, and then you'll probably start to get a hang of it, because it might be quite abstract. So yeah. So now what I'm doing is to take two polarized sheets. Don't look at the diagram now. We're discussing case one also. Let's have two polarized sheets, both in the zero direction, vertical direction. I pass a beam of photons, basically light, and I see light comes out. Photon is led to. So what happens in the second case is that I give the second sheet a 90-degree rotation. Now it's horizontal. And when I keep them, when I overlap them, what I see is that the photon is not led through, it's absorbed. So that obvious 90-degree rotation, that change in the measurement direction, has led to the change in your measurement as well. And let's just extend this experiment to the third polarized sheet now, just to explore. So what you see is that let's take the third one and keep it in between these two guys at a 45-degree angle. What do you think will happen? You see it's not very obvious and intuitive, but what you see is that at the intersection of the three polarized sheets, you see that some light is led through, right? That's very interesting. It's one of the most interesting experiments in quantum physics, and what we want to convey from these two experiments is that if you have the same kind of conditions of measurement in your experiment, how many ever times you repeat it, you're going to get the same results. But if you change something in the condition of measurement, you're obviously going to get different results. So in the case of the spin, we change the direction. In the case of polarization, we change the angle. So what do we change for qubits to change the measurement? That is what is called basis vector. We'll be discussing it in just a bit. But before that, let's see what qubits are mathematically, and let's give it a formal definition. So as I told you, qubits are definitely a matrix, right? And it's of the form that you can see on my screen now. And we just want two conditions to be satisfied, that A and B, which are part of the matrix, is their complex numbers, and their sum of their squares should be 1, normalization, right? What is very interesting here is to note that there is something called the Dirac notation that we make use of to represent these mathematically, represent qubits mathematically. And of course, I'm sure you'll be familiar with the Bra and the Ket notations. That's what's the Dirac notation from quantum physics. And this is what I was talking about in the previous slide, standard basis. The Ket B1 and the Ket B2, when you change these two vectors, that's when your measurement of the qubit also changes. So, and you have to know one thing, B1 is the zero qubit and B2 represents the 1 qubit. It's just a convention and something we should just make note of. That's it. So what have we learned until now? We saw vertical measurements, we saw horizontal measurements, and we saw an arbitrary general angle theta. And of course, we saw the theta equal to 45-degree measurement in our polarization experiment. So this is just a summary in matrices, all right? Right. So coming to the interesting part of it all, we have largely two kinds of quantum computers, which are very interesting, especially to me. So superconducting quantum computers use what is called the superconductivity principle to operate. What essentially happens here is that you store a qubit in the dilution fridge, which exists at the absolute 0 degree, and Kelvin, sorry, and that's when you perform your operations. So very leading experts from IBM, Google, and UCL, colleges like UCL, they are performing a very extensive research in this part of quantum computing. And very interesting part of quantum computing is what is called the trapped ion quantum computer. This is very interesting, especially, of course, to physicists. But what happens here is very interesting. You trap your qubits in ion traps and manipulate them with lasers. And very interesting research and inspiring research is being carried out by startups like IonQ, NUSCQT, and MIT, and many more organizations and universities, of course. So that's just to give you an idea of the two junctions that you might come across when you start to learn quantum computing. Yeah. So having come until this, how do I make sense of qubits? How do I diagrammatically represent them? How do I understand them mathematically? Because this is a very abstract concept. So let me help you out with it. Okay. So single qubit systems like we saw now, just one qubit, 0 or the 1 qubit. That's just represented by your Ket notation. And what's more confusing is the multi-qubit systems. Let's make it simple. Let's say I have a quantum computer. I have 10 qubits in it. It's just an arbitrary number. You don't have to worry about that now. But let's say 6 of them are 0 qubits and 4 of them are 1 qubits. How do I make sense of this? How do I mathematically put it forward? Right? So we use something called the tensor product for this. And what essentially that means is that quantum computer consists of a tensor product of 6 zeros and 4 ones. So that's how you make a sense of what multi-qubit systems are, a number of qubits, right? So let's go on to talk about the diagrammatic representation of qubits here. There are 2 representations that I find very interesting. So one of them is the line representation, and you can see this very much in most of the online simulators, quantum computing simulators like IBM Quantum Experience, which is on cloud, and also Quark. And what it means is that one line represents 1 qubit, and it's a convention that it's labeled 0 qubit, but of course it can be 1 qubit as well. So the second one is what is more interesting and what is more intriguing for physicists. And of course, the students who are studying physics might find this very interesting. But what I'm doing here is to take a 2-level atom. Of course, a 2-level atom doesn't exist. What I'm trying to do is to take an atom and consider 2 levels as my system. So in that system, what I take is that the ground level to be the 0 qubit and the excited level to be the 1 qubit. So this is one very nice representation and will be helpful when you go into the physics part of quantum computing. Right. So we have done qubits. Great. That's just one part of the system. What next? We use what are called gates to compute all those qubits. So in this particular diagram here, what you would have noticed now is that I have 3 qubits. And I have these little boxes named labeled A, B, C, D, E, and F. What are these? These are what are called gates. And of course, this is the quantum counterpart of the classical gates that you know, right? Just like that, logic gates. And what is one thing which is very interesting about them is that just like our qubits, they are also characterized by matrices. And just to go in a little bit deeper, we use this particular convention 2 to the n, 2 to the number of qubits to find the the nature of the matrix. So A, B, C, and F are working on 1 qubit each. So what happens is that you consider 2 to the 1. So it's a 2 by 2 matrix. And when you see D and E, they're working on 2 qubits. So 2 to the 2, 4, and we have a 4 by 4 matrix. So this is essentially, it follows from the fact that you want your condition of matrix multiplication to be true. So when you have when you have a gate with 3 qubits working on it, you will have a 2 to the 3, 8 by 8 matrix, correct? So what you see here is what is called a quantum circuit that I will be coming back again, but just a minute, all right? Hang on. So yeah, let's introduce you to some of the most popular gates that we will come across when you start, exploring this field. Of course, there are many more, but I'll tell you most common ones, right? The Hadamard gate, the Pauli XYZ, the phase gate, and we have a special case of phase gates wherein we have the S and the T gates. We have something called the C0 gate, and all these look complex. They might look complex. Quantum computing in itself might look complex, but it is not. And I'll tell you why. Because quantum computing is just merely matrix operations using these matrices, which are called unitary matrices, which means they're orthonormal, and they also might have complex number entries. And for the math enthusiasts out there, what it means is that if I'm given with a matrix A dagger will give me an identity matrix, which means the complex conjugate of the matrix and the matrix, the product of them will give you the identity matrix. So everything boils down to literally matrix operations here. And what I want you to know is that matrix operations, qubits, gates, which builds you a circuit, And then you make newer circuits, and you explore with them. You play around with the gates to explore with them, and then you want to explain this using an algorithm. So matrix multiplications and other matrix operations at the heart of it, of quantum computing. You go beyond and beyond and beyond, and you end up at an algorithm. So that is what quantum computing is all about. It might seem complex, but as I told you, it's one of the most easiest and most beautiful subjects to learn. All right, so we come to the end of the technical part of it all. So let's see, hey, why should I pursue quantum computing at all? And I will give you just one answer. This is a line from my book. For questions we don't have answers to, and for answers we don't have questions for. And what I mean by this is that there are so many open questions in quantum computing waiting for you to come and solve them. And of course, answers. By the second line, what I mean is that there are fields, new fields waiting there to emerge, to be discovered, and quantum computing might lead to the emergence. So what I want to urge you to do is to explore quantum computing, find beauty in it, enjoy it, find new answers, find new questions. So we come to the end of the talk, so I would just like to talk about what we do at SheQuantum. We are a e-learning platform, and we focus on teaching quantum computing at its simplicity without losing any rigorousness mathematically, of course. And we have the objective of connecting more women to quantum. See, guys, in science in general, in research, STEM, anything that you see, women takers are less, and this should change. I personally feel when I talk to women scientists who are working in quantum computing, one thing they keep repeatedly telling me is that there is not much representation in the company that I'm working in or the university that I'm working in, and that it should change. Also, student takers for quantum computing, there are more men. I'm not saying it's a wrong thing. It's absolutely great. Both the genders, all of the genders should take it up. But I feel especially women should take more part in it. So we do three things at SheQuantum. We inspire people to take up, especially women, to take up this field. We tell the perspectives of this field. We show the scope, and we have interviews and interesting videos of experts and professors, researchers in this field who tell their part of the story, how they started quantum computing, what kind of problems they faced when they started to pursue research in this field, and how they overcame it. And that is what's most inspiring of everything, right? And the second thing that we do is to educate. We are, of course, the e-learning platform, and we have many lecture series in quantum computing, quantum information science, quantum physics, and many more. And I really insist that you pursue all of them at www.SheQuantum.org. It's our platform. I'm sure you will benefit from it. And of course, at the end of it all, what next? Right? Opportunity. And that is where we pitch in again. And we help our users find, and we provide them with research, internships, and job opportunities after they complete their courses with us at SheQuantum. And what I would like to say is that each and every one of you sitting here should definitely take up the challenge of learning quantum computing through SheQuantum. And definitely, I'm sure you'll be able to contribute to this field. Anybody can contribute to this field. And yes, thank you very much. And I'm open for questions. Any questions?
From our participants. So first question, does the property of simultaneous existence of 0 and 1 makes quantum computers more secure from hackers?
Sorry, I didn't hear the last part. Could you repeat it, please?
The property of simultaneous existence of 0 and 1 makes quantum computers more secure from hackers.
Right. Okay. This is one very prevalent thought in most of the articles on the internet. It is not completely true. See, the thing is, kind of quantum computers that we have now cannot do that because they aren't fault tolerant, which means that they are not the ideal quantum computer that we want. We, in a way, theoretically, ideally speaking, you're correct. But we have a long way to go. Yeah, next question, please.
Software engineers know how fast the environment's changing, whether it be AI, ML, or cloud. So the attitude has been to learn it, but is quantum computing similar or even more disruptive technology?
Of course, every technology has its pros and cons. And as of now, don't worry about quantum computing being a disruptive technology. It's not that we are not there yet. So I urge you to take quantum computing just like AI, data science, ML, and learn that too, because it can add a lot of value to your life itself. And it's as actually not even as much as AI and ML, it's even more prospective and can open up a lot of opportunities for your life. Yeah. Next question.
Things like quantum laptops will be possible.
Sorry, I didn't get that.
Quantum laptops be possible.
Sorry, I didn't get that. Quantum, what's possible?
Like, I mean, they are asking if is the technology could be scaled down so that the general public could even have it, use it in the future.
All right. So for general public as such, I would say there are simulators available online like the IBM Quantum Experience that you can use. Even Quark is a very nice piece of software. And if you're talking about a commercialized quantum computer, we are still in the very early stages. Quantum computing is still a baby. You have to wait for him to become a handsome young man, and then you have to wait for him to become a matured young man to bring in commercialization. So yeah, again, I would like to say we are not yet there, but I don't think that is the aim as well. The aim is to carry forward research in this, and I'm not even quite sure whether if it's commercialized for the normal user, whether it will be useful except for research. Right? Yes. Next question.
Mechanics should one know to get started with quantum computing?
Well, what should you know to get started with quantum computing? Is that right? I'm sorry, could you speak a little bit louder? I'm missing out some words from your question.
How much quantum mechanics should one be knowing to get started with quantum computing?
Right. Okay. See, it's only the basics, I would say. You should kind of understand because see, quantum computing itself is not very intuitive. It's not an intuitive subject. So is quantum mechanics. So I feel that it's good to equip yourself with the basic principles like what's superposition and what's entanglement. Just know a good amount of physics. I'm sure if you're doing an undergraduate degree in engineering in India, of course, you have enough of physics to carry forward your research and studies in quantum computing. And of course, I will tell you, it's not that only if you know quantum physics you can understand quantum computing. It's just that you should know a little bit about it. Yeah. Next question.
Adopted AI and cloud in their courses. Should quantum computing has reached a state where it would be worth to add it as well with the quantum mechanics courses in the college syllabus?
Absolutely, yes. And you know what? Actually, undergraduate degrees are not available in quantum computing now, except one university, and I think it is the University of Chicago. But I think it should be, we should catch them young. You should start learning quantum computing at your high school level, I feel. And, that's when you know whether you're interested in it, and it helps you broaden your horizons. Of course, because this is a highly interdisciplinary field, anybody can learn quantum computing, and I feel yes, it should be made a part of the curriculum. Yes, it is a part of. Yeah, I should mention this one. It is a part of the computer science and physics curriculums in some universities abroad, but it's just one module, I guess. It should be extended more. Yeah. Next question.
Question is, as a person is software engineering or IT, how could one shift to quantum computing for like basic what is the basic career path one should follow?
Awesome. So for a software engineer or a person who's doing that computer science or software engineering degree, it's one of the best things to go for quantum computing, because what you need is just a little bit of equipment in quantum mechanics. And see, quantum software development and algorithm development is basically a lot of mathematics and Python. So we use a framework called the Qiskit. That's the most famous one. It's owned by IBM, and it's open source. So I would say anybody who's into software should definitely go explore what Qiskit is. And it takes you just one thing: you should know Python and you should know mathematics. Yes.
Challenges are quantum computers facing right now?
Sorry.
Quantum computers facing right now?
Sorry, I just got quantum computers facing right now.
The sort of challenges that the quantum computers are facing.
Yes, wonderful question. The kind of challenges that we are facing now is scalability. What I mean by that is the number of qubits that we want for the quantum computer. See, I told you 2 to the power n qubits, n number of qubits will give you the many number of parallel computations, right? So more the qubits, more the efficiency. That is our current theory. And what we're having problem in is to create effective non-faulty qubits. And now, of course, IBM is planning. IBM has a 65 qubit computer as of now. And don't get, like, of course, I talk more about IBM because they are the most prominent leader in this. So yeah, just taking general case of IBM, there is a 65 qubit computer, but they are planning for a 1,000 plus qubit computer by 2023, and we are still at only that number. We don't have millions of qubits. And essentially, what our theory says is that if we are able to build so many millions of qubits, your efficiency will also increase. So that is where our problem lies currently. And of course, even if we achieve that, there will be more problems wherein we have to secure our communications. And because now we have a computer. What happened when we built a normal computer is that next, how do we secure our communications? How do we handle so much data? That is not, how do we handle so much data will not be a problem in quantum computers, but there are many different challenges, not only now, but also after an ideal quantum computer should be. Next question.
For answering all our questions.
Oh, great.
Okay, ma'am. There is one question from my end, which is asked by,
yes,
which is a participant. Like, what
yes,
are
please.
some of the real world problems that we will be able to solve, and if what would be the advantages we will have if we develop quantum computing technology? Like some
Great.
example.
That's a wonderful question, and just the most important question of this session actually, because what can we do with it? That's the main thing, right? So as I mentioned in my talk also, it's very helpful in drug discovery. As in, if you want, let's say you want to cure an XYZ disease, and you want to do it fast. We, with our current computational powers, even supercomputers cannot establish it in a very good, let's say, a good amount of optimal time. So I think one of the most interesting and practical applications of this field is drug discovery. To be more precise, let's say, let's take the example of COVID-19 itself. Let's take COVID-19 vaccine. If at all we had a quantum computer, ideal quantum computer, an efficient one, we would have been able to find a vaccine much more sooner. So that is the idea, and it's not only limited to that. So it also has a lot of applications in chemistry, wherein you can discover newer molecules using quantum computers. Because the quantum computer itself is its base lies in quantum mechanics, and quantum mechanics and quantum chemistry are very close by. So that will help in finding new chemical compounds as well. Yes. I hope that answers was
One and only question, and now I think we do not have any more questions. So,
great. Yes,
we are
thank
very
you. And I would just like to conclude that, with saying that you can always contact us on that email ID that you see below, and we will be happy to help you out. And I urge you to explore SheQuantum and quantum computing in general. So all the best to every one of you. Do consider taking up a career in quantum computing. Thank you.
Thank you so much for the informative session. Now we'll be moving on to our next keynote speaker shortly, so be patient.